All right. Next, I'd like to discuss the binding energy of nuclei. Nuclei are very, very strongly bound. It takes an enormous amount of energy to take a nucleus apart into its component particles. In fact, the energy is so large that we can measure it just by measuring the mass of the nuclei. 1 second. All right. So to find the binding energy of atomic nuclei, we nearly need to calculate this from the mass difference. And what I mean by this is the mass difference between the nucleus and the component particles, okay? So that the binding energy is equal to the mass of the constituents minus the mass of the nuclei times c squared, okay? And we can write this as follows. It's simply Z times the mass of a hydrogen atom plus the neutron number times the mass of a neutron minus the mass of the nucleus that's going to be produced out of these. Okay? And if we write the mass in terms of the atomic mass unit, then we can figure out the energy just by multiplying by mc squared for an atomic mass unit, which is 931.49 mega electron volts. And that's it. By the way, you notice we've included here the mass of a hydrogen atom, not of a proton? The reason we've done that is that, first of all, one can measure the mass of a hydrogen atom very, very accurately. But secondly, because doing it this way, we automatically include the mass of the electron in the atom, and then we can use the mass of the neutral, atom that results here, okay? Okay, just for an example, let's look at the binding energy of a deuteron, which is just an atom of a heavy isotope of hydrogen with a mass number of 2. In other words, hydrogen that contains a proton and a neutron in the nucleus. The mass of the hydrogen atom is 1.007825 times U. The mass of a neutron is 1.008665 times U. And finally, the mass of a deuterium atom is 2.014102 U. I need to include all of the significant figures that I can get for these masses because the differences between the masses are so small that a lot depends on the least significant figures. I need to include all the significant figures in order to get an accurate result. So now we can just put these values into the calculator and calculate the mass difference. Excuse me. And what we find is that the masses almost cancel out, but not quite. So the mass difference is 0.002338 U. So we'll multiply 0.002388 times 931.49 mega electron volts per U. And this works out to be 2.22 mega electron volts. Okay? Or if you like, we could write this as 1.11 mega electron volts per nucleon. Okay? Very good. Well, that was straightforward, right? Here, let's do a second example. Let's figure out the binding energy for a helium nucleus, a helium-4 nucleus. Which consists of 2 protons and 2 neutrons. All right. It's not very different. The only additional piece of information we need is the mass of a helium atom. So and the mass of a helium-4 atom is simply 4.002603 atomic mass units. So using that and what we've already written down, go ahead and find out the binding energy, calculate the binding energy per, the binding energy for a helium-4 nucleus, and then go ahead also and figure out the binding energy per nucleon. Which here would just be EB divided by 4. All right. I'll check back with you in just a moment. So I expect that what you found is that for helium, the binding energy is 28.3 mega electron volts, or 7.07 mega electron volts per nucleon. And what's interesting, I think, is that this number is much, much larger than the binding energy per nucleon in deuterium. Okay? So some nuclei are much more strongly bound than other nuclei. In fact, it's interesting at this point to look at the binding energy per nucleon of all the stable atoms. And so let's take a look at that now. Very good. Here's the chart. So it's interesting to see that the binding energy per nucleon starts out, has this form. It's relatively small for light atoms, although helium-4 is an exception. Then as we go to heavier and heavier atoms, larger and larger mass numbers, the binding energy per nucleon goes up and up. And finally, it reaches a maximum for atoms near the mass of iron. And then as we go to still heavier atoms, it goes down. So very light and very heavy atomic nuclei are unstable. Okay? That is, we could release energy if we could take them apart and rearrange the nucleons to make atoms of intermediate mass. Okay, so that's an interesting result. Important too, of course. Okay, well, finally, I'd like to talk about the force that holds nuclei together. Okay? Here's our cartoon picture of a nucleus again, containing protons and neutrons. Now, remember, protons are electrically charged and they repel one another. So it's clear that there must be a tremendously strong repulsive force between these protons because they're so close together. And remember, the Coulomb force goes like 1 over r squared. And yet some other force is holding it all together. This other force is called the strong nuclear force. And we can say a little bit about it without going into details at this point. First, the strong nuclear force acts between nucleons. It acts between protons, between neutrons, and between protons and neutrons. As far as can be established, the force is charge blind, meaning that the force between two neutrons or between a neutron and a proton is the same as the force between two protons. It acts between nucleons and it's independent of electric charge. It's not the Coulomb force, but something else. Secondly, the nuclear force is very short range. This is a sketch of the potential energy that a neutron feels in the vicinity of another neutron or a proton due to the strong nuclear force. The force is very short range. Beyond about 3 femtometers, it's negligible. But as this comes closer, there's a tremendously strong attractive force, and then a minimum, and then repulsive force. So this tremendously strong attractive force results in an equilibrium distance between the nucleons of about 1 femtometer. Okay? Here's the total potential energy for a proton-proton pair. It looks almost exactly the same, but not quite. What's the difference? Remember what I just said. This is the total interaction. So it includes both the nuclear force, but also the electrostatic force. The electrostatic force is strongly repulsive, and yet, on this scale, it's just a small correction to the very strong nuclear force. The electrostatic force is also long range. So you can see that if I have two protons, as I bring them together, they'll feel a repulsive force. The repulsive force seems tremendously strong, but once I get them closer together than about 4 femtometers, then the attractive strong nuclear force will take over, and then they'll be attracted together. Okay? All right, so that's just sort of the basic experimental facts about atomic nuclei and about the strong nuclear force. Let's stop here.